Hey everyone, welcome to Info 8 Univu, where we explore everything about space. I am Aparna Oja, and today we are talking about Delta V budget for launch vehicles, a key concept in rocketry and orbital mechanics. We'll bring it down, explore real world examples, and see why it's crucial for reaching orbit. Stay tuned and let's dive in. Don't forget to subscribe for more. We need to know what is delta V. So delta V means change in velocity, and it is used to measure how much a rocket can change its trajectory or orbit. It is typically measured in meters per second. Delta V is a much more useful way of measuring the range of a rocket, since in space there is no force to slow down a rocket. This means a rocket can orbit indefinitely, making traditional distance measurements impractical for determining rocket range. So delta V, how it is calculated? We have different versions of this formula for the rocket equation, and however, the simplest form of the equation is delta V, which is equals to specific impulse of the engine into standard gravity of the body being orbited or launched from, into the natural logarithm of wet mass divided by the dry mass. Here is what the components represent. A specific impulse (ISP) refers to the efficiency of the rocket engine. Standard gravity G0 is the gravitational acceleration of the celestial body, such as Earth's gravity, that is 9.81 meters per second square. What is m0? Wet mass. It is the total mass of the rocket including fuel, and mf is the dry mass, which is the mass of the rocket after the fuel has been consumed. It's important to note that this equation does not account. So now we need to know about the delta V budget for launch vehicles. What is it? The delta V budget is a summing up of the losses that have to be overcome by the launch vehicle in order to get into the orbit. We have to get to a desired velocity, and the propulsion system must achieve that velocity plus make up for losses from drag and what's called gravity losses. But there's also a third loss called the steering loss. Let me try to explain what that means. So here is our rocket. The rocket is launched at first straight up to clear the tower and to get high in the atmosphere. Then it starts to pitch over in order to start velocity along the downrange direction so that it can finally achieve orbit. But in the optimal steering law, it turns out that the rocket will actually pitch downwards near the end, which is not along the current velocity vector, and that results in some losses that have to be made up by the propulsion system. Let me explain this in more detail. So here we can see what do we mean by delta V steering loss. Let's consider the optimal trajectory that takes a spacecraft into orbit. Let me draw my axis where this is the downrange distance and this is the altitude. We have a desired altitude and velocity. So let's say this is the altitude we want, and we'll draw in a vector here representing the desired velocity. We launch the rocket on an optimal trajectory. It will follow a path that takes it all the way up to the altitude and velocity we need. Now to consider that what we mean by steering losses. Imagine the rocket launching at first directly vertically, then it starts to pitch over and follows the optimal trajectory that gives us the minimum propellant to get into orbit. Well, it turns out that the rocket has to tilt or pitch over, and is sometimes even pointed towards the ground near the very end, in order to cancel out the vertical momentum we picked up during the launch. At any point during the optimal path, the velocity represents the trajectory. Because of the optimal steering law, the rocket is not necessarily pointed or aligned with the current velocity vector all the time. This misalignment between the thrust and the velocity vector accounts for certain so-called cosine losses. The thrust is not delivered entirely to add to the velocity, and that is where we get the velocity steering losses. By the way, in the case of launching the Lunar Excursion Module from the surface of the Moon into orbit, the angle at the very end for the thrust vector was a -4 degrees. The steering loss, delta V steering loss, for the Saturn V was 243 meters per second. So, our propellant has to make up for that loss. That is very difficult to calculate, and one practical way of approaching this it is to look up the steering losses on similar launch vehicles. Let's discuss some list of velocity losses that must be accounted for in order to size the propulsion system of your launch vehicle to achieve the desired orbit. So here we are taking the example of Saturn V launch vehicle, the largest ever built in terms of payload capacity, sent men to the moon. It had an excellent safety record with all 10 flights being successful. This vehicle stood about 360 feet tall, 111 meters, and carried 285,000 pounds, that is 129 metric tons of payload into LEO. It also delivered approximately 50 tons to the moon. The first stage of the Saturn V used kerosene and liquid oxygen as propellants, yielding a specific impulse of about 264 seconds. The second and third stage utilized liquid hydrogen and liquid oxygen, achieving a higher specific impulse of approximately 435 seconds. Most calculations for launch vehicles like this are performed in the International System of Units, that is the SI unit. The Saturn V carried the Apollo capsule, which included the Command Module, Service Module, and the Lunar Excursion Module. It initially achieved a circular orbit around Earth at an altitude of 176 kilometers, that is 110 miles, before being sent towards the Moon. In analyzing the trajectory of a launch vehicle into orbit, we consider the problem in xy coordinate with the downrange distance x-axis and altitude y-axis. The goal is to achieve the desired altitude and velocity vector. This problem involves determining the best trajectory to minimize propellant usage while delivering the payload into orbit. Initially, the rocket is launched vertically to clear the atmosphere, reducing drag losses. As it ascends, it gradually steers horizontally to achieve the required downrange velocity. Near the end of the burn, the rocket may point slightly downwards to ensure proper orbital insertion with the desired velocity vector. Now, to analyze this process, a simplified mathematical model is developed. In this model, thrust is assumed to align with the current velocity vector. The forces acting on the rocket are thrust, weight, and drag. Drag opposes the velocity vector, while weight has components acting vertically and along the velocity vector, influenced by the angle gamma between the velocity vector and the local horizontal plane. Here, using Newton's law The net force along the velocity vector is calculated as F equals to ma, which is m dv by dt, which is equals to t minus d minus w sine gamma, where t is thrust, d is drag, weight is w, and m dv by dt represents the change in velocity over time. This simplified model is essential for understanding the trajectory and propellant requirements, while accounting for velocity losses from drag and gravity. Here, some calculations. So if we divide the mass m into the right side and then multiply by dt, everything on the right, then we have this equation dv by dt, which is equals to t minus d minus w sine gamma, all divided by m. Now we can put integral signs on both sides. On the left side, we integrate from the initial velocity v0 to the final velocity vf, and on the right, we integrate from the initial time t0 to the final time tf. The integral on the left becomes vf minus v0, which is equals to delta v. Here, taking our equation further, we find the desired velocity v as t over m dt So this following equation comes, where we get the integral on the left becomes v minus v0, which is equals to delta v, and the equation further we find the desired velocity. We can look the huge equation. This represents the velocity provided by the propulsion system via thrust. Here we can see, assuming an initial velocity of 0, we get the final equation. The first term is thrust-induced velocity, the second is the drag loss, and the third is gravity loss. W over m represents the local gravitational acceleration, which decreases with altitude. Rearranging, we find delta V prop, which is equals to V desired plus delta V drag plus delta V gravity. This equation includes the velocity the propulsion system must supply and the additional delta V to overcome drag and the gravity losses. Is this the whole story? No. So now we have to further consider some simplifications and considerations. This analysis simplifies many aspects of the problem, real world problem. So real world considerations include, firstly, the Earth's rotation at the equator. Earth's rotation provides approximately 1000 meter per second eastward velocity. Second, steering losses. These arise when the rocket's thrust vector is not perfectly aligned with its velocity vector. Third, we need to know thrust misalignments. Errors or intentional out-of-plane maneuvers can introduce inefficiencies. Ambient pressure effects. Atmospheric pressure decreases with altitude, increasing rocket efficiency at higher altitudes. Now, here is the Saturn V example again. We are referencing from the Space Propulsion Analysis and Design book by Humble, Henry and Larson. The Saturn V's velocity requirements include desired velocity for low Earth orbit (LEO), that is 7,798 meter per second. Contribution from Earth's rotation will be minus 348 meter per second. Gravity losses, we have 1,534 meter per second. For drag loss, we have 40 meter per second. For steering loss, we have 243 meter per second. So the largest contribution is the desired velocity for LEO, which is straightforward to calculate. Gravity, drag, and steering losses are generally estimated via simulations or historical data. Now, let's do a single stage calculation for the Saturn V. The propellant mass for a single stage launch vehicle is given by this equation. So we have propellant mass on the left, we have payload mass on the right, and we have a bunch of other stuff such as the delta V of the propulsion system, we have an exponential, the ISP, and the gravity. That is the standard gravitational acceleration for free fall. So G. And we have something called the inertial mass fraction, F inert. That's basically telling you how much structure mass you have compared to a structure mass plus propellant. On the bottom, we have 1 minus the F inert times this exponent. This equation is also on the book mentioned above. Before we put in a lot of numbers, let's just look at what happens downstairs. This is the denominator. Whenever you have 1 minus x over something, you have to be careful that x never becomes 1, because then you would have 1 over 0, which would imply you would need an infinite amount of propellant. So if we are using a formula like this, we should ensure this number downstairs is not 0. We should also ensure it's not negative, because in some case negative is even worse. There's no such thing as negative propellant. You might wonder, well, what does that mean? It's important that engineers interpret their equations. So what do the equations mean? What are they telling us? And are they logical or illogical? Are the equations not relevant to this particular problem? Or are they indicating something's breaking down? So these are important issues whenever you make math models to solve problems. This equation is telling us something that's actually true. If the denominator is 0 or negative, it means that we would have the launch vehicle you are trying to design is infeasible. How can we check that before diving into the details of calculating the equation? Well, if we look at the denominator and set it to 0, we notice as ISP gets smaller, this exponential term will become a bigger number, which leads to a negative value quicker. If we set this equation to 0, we can find ISP is equal to delta V over the log of 1 over F inert times G. If ISP is less than this value, then we have infeasible conditions. Equality means the propellant is infinite and a value less than that implies negative propellant. Both cases are infeasible. This is something to check before going further with complicated equations. So we took an example of Saturn V rocket. The first stage of the Saturn V used kerosene and liquid oxygen for propellant with an ISP of 264. We find ISP, which is equal to delta V over the log of 1 over F inert times G. If ISP is less than this value, then we have infeasible conditions. Equality means the propellant is infinite and a value less than that implies negative propellant. Both cases are feasible. This is something to check before going further with complicated equations. Here, the first stage of the Saturn V used kerosene and liquid oxygen for propellant with an ISP of 264 seconds. The inert mass fraction usually ranges from 0.05 to 0.1. In other words, about 5% to 10% of the mass of the propellants plus structure is structure that's basically the tank and other components holding everything together. In fact, 5% is a very small value and hard to achieve, but we'll assume it optimistically just for the calculation with the Saturn V. The exact value of G for the free fall of 9.80665 meter per second square. This is a defined quantity with no number after the 5 and should be used in all propellant mass calculations. Plugging into our equation, the delta V required for the propulsion system is 9267 meters per second, which we had in the earlier budget. Now, putting the values into the infeasibility test, we check whether ISP is less than this value. We have 9267 meters per second upstairs, the logarithm of 1 over 0.05, and then times the standard freefall G. This gives a value of 315 seconds. However, we had used an ISP of 264 seconds, which is smaller than 315 seconds. Therefore, we have an infeasible case or a non-feasible condition as stated in the book. How do we fix this solutions? So possible solutions are improve the ISP by using a bigger value for the specific impulse, reduce the inert mass fraction to less than 5%, use staging instead of one stage or two or three stage. The Saturn V used 3 stages. It achieved higher specific impulse by using liquid hydrogen and liquid oxygen in the second and third stages. The F inert value was little bigger than 0.05, which was an optimistic assumption in this calculation. That concludes our discussion on the delta V budget for the launch vehicles. I hope you liked the video, and with this, signing off, sayonara. This is Aparna Oja.